Hey, before we start, I just want to give a special thanks to Zach and Jonah for the new outro song. Thank you too so much. Okay, as we all know, the Laplace transform of little f of t over t is equal to the integral going from s to infinity of capital F of u du, where the capital F of u is just the Laplace transform of little f of t. But have you guys ever wondered, so what? Well, in this video, I will tell you guys, so what? Especially if you like integrals a lot, then you should definitely know this right here, because you can come up with a lot of nice integrals based on this. For example, maybe you guys have seen the integral going from 0 to infinity of sine t over t, done by this guy.
Man, that guy took like half an hour or something like that, and he was talking too much. I don't like that. But he ended up with a correct answer though, pi over 2.
However, if you guys want to check that out, go ahead and do it. The link will be in the description for your convenience. But anyway, that was okay. But have you guys ever wondered, what if we have the integral going from 0 to infinity of cosine t over t instead? Unfortunately, I have to tell you, that integral does not converge. Sorry. This is how we can do that integral. Here we go. First, let's consider the Laplace transform, and we are talking about 1 minus cosine t over t, right? Well, I want to show you an integral, but why am I bringing up the Laplace again? Because remember, by definition, this right here is equal to the integral going from 0 to infinity of e to the negative st times this, which is 1 minus cosine t over t dt. If we can figure this out, just an expression in the S world, that would be so nice, isn't it? Because, you see, just go ahead and let s equal to 0 right here, then that will be 1, and we will get that integral that we want. In fact, you can plug in a lot more s value to end up with like some really cool integrals. That's the idea. But the problem is that I don't think you want to do it from scratch right here. Don't be like that guy in the video I mentioned earlier. So this is how you are going to do it right here, right? So here we go. First, we have to figure out the Laplace transform of just the top, the little f of t. And in our case, the little f of t is of course just this, namely 1 minus cosine t. So have a look. The Laplace transform of 1 minus cosine t, right? Let's see what this is. And hopefully you guys have seen my Laplace transform marathon video already, right? Okay, here we go. The Laplace transform of 1 is 1 over s. But, you see, we are using u, right? We're using u for this version because later on we have to integrate this from s to infinity. So instead of 1 over s, we will be putting down 1 over u right here, right? And then minus the Laplace transform of cosine t, which is s over s squared plus 1 squared. But again, we're using u, so it's u over u squared plus 1. Again, check out that Laplace transform marathon video. The link will be in the description for your convenience if you need to review on all this. In fact, this is the last question I proposed, and then that's why I'm doing this for you guys. All right, let's go ahead and clean things up if you would like. I would like that, of course. Let's go ahead, get a common denominator. So I need to multiply this and that, and I will just have u to the third power plus u. On the top, I need to bring this right here, which is u squared plus 1, minus u times u, which is u squared. All in all, we just get 1, right? So, as you can see, this is our f of u. Now we will come back here. Based on this formula, all we have to do is that this Laplace transform is just nicely equal to the integral going from s to infinity of f of u du, and you picked out the f of u right here, which is 1 over u to the third power plus u du, like that, right? Very nice. Do not go do this, right? Do not do this by itself, right? Life doesn't have to be that hard sometimes. This is much easier to handle. How can we integrate that though? Let me show you guys this way. Let's go ahead and factor out u to the third power on the bottom. Why? Because it's going to work out so nicely. Why? Because you'll see. like this, yeah? Well, this is u to the third power on the bottom. Let me bring that up. You will see that this is the integral going from s to infinity, and we have u to the -3 on the top, right? And then over the bottom is 1 plus u to the -2 du. Why is this so good? Yes, because the derivative of the bottom is precisely -2 u to the -3. And we do have the u to the -3 on the top, so you don't have to do the partial fraction. In fact, if you do the partial fraction, get this. But this is cooler if you integrate. You'll see why. Anyway, go ahead, let's multiply this by -2, but we also have to divide it by -2, so that you can see this is the derivative of that. Anyway, though, just integrate this on your own also. You get -1/2, and then we have ln parentheses because this is always positive. All right, and then we have to plug in s to infinity. And the reason that I prefer to do it this way is because it's much easier to plug in infinity right here. Infinity to the -2 is just 0, and we get ln 1, which is 0. So when you put this right here, you will see the first part will be 0. So we will end up 0 for the first term, and then minus, you put s in here, which is -1/2, ln of 1 plus s to the -2 power, like this.
So now as we can see, this right here is equal to that. And of course, this is equal to this integral, so we can say this integral is equal to this. Then I will of course write this down right here for you guys.
Like this. Then all you have to do is pick your favorite s values, but you have to be careful though. Because for example, if you let s to be 0, unfortunately, you cannot have that right here because you get 0 to the -2. That right there does not work. And s cannot be negative numbers neither, because otherwise this integral doesn't even converge in the first place. So you can just pick some s values that you want, but you have to make sure that this right here converges. Well, let's do an easy one. Let's do the one that I mentioned earlier. All we have to do is let s equal to 1, because that, you will see, on the left hand side, we get the integral going from 0 to infinity. We get e to the -1t, which we can bring that down to the denominator, and we just have 1 minus cosine t over t e to the positive t dt. And then on the right hand side, all we have to do is to put the 1 right here, so we get 1/2 ln of 1 plus 1, which is ln 2, like this. That is it, right? Very good, huh? And of course, you can just try to do with other ones if you like. You can put a 2, 3, 4, 5 whatsoever, but this is it. And the idea is that you might want to do the Feynman's technique with this right here, but the better thing is generalize this, which is from the Laplace transform, and you can just use that. Very nice, right? So anyway, that's it.
Black pen, red pen, black pen, red. But he's a calculus teacher, uses black and red. He does math for fun. If get done using complex numbers, doing marathons. And as always, that is